Welcome back. Problem 1-84. This problem is taken from chapter number 1, that is stress, and the book name is Mechanics of Material by R.C. Hibbeler. Statement is the frame is subjected to load of 4 kN which act on member ABD at D. Determine the required diameter of pins at D and C if allowable shear stress for material is 40 megapascal. Pin C is subjected to double shear, whereas pin D is subjected to single shear. So you can see this is the frame, clear, that is acted upon by 4 kN load at point D on this member ABD only, clear. So this, given that this C, there is a pin which is acted upon by double shear, and at point D the pin will have a single shear. So you have to determine the diameter of pin at D and C. So let's start with the solution. What we will do is that we will take this member ECD and we will draw the free body diagram. So first let me draw it first. So this is the member, clear. There is a point C over here, and at this point we have point D, clear. And you can see there is a roller support at point E. So when you remove it, so you'll be having reaction force which will be in upward direction. Let this is NE, clear. This is your point E and this is your point D, and there is a pin support at point D, clear. So when you remove it, so you'll be having a reaction force, along horizontal. Let it be like this. This is dx, and you will be having a vertical reaction force which is taken upward, and let this is dy. At this point is point C. So you can see at C there is a member. So if you remove this member, so you'll be having a force which will be equal to FBC, and this FBC makes an angle theta with this horizontal. So what we will do is that we will find this theta. Distance between this E and C is 1 meter, clear, and distance between from C to D is 1.5 meter. Okay. Also, if you look at this figure, so this is 1.5 and this is 1.5, and this is the theta angle. So this theta will be equal to, if you take, let this is theta angle. So if you take tangent of theta, so this tangent of theta will be equal to perpendicular, which is 1.5 divided by base, which is 1.5. Clear? So theta is equal to tangent inverse 1, which is equal to 45 degree. So this theta is equal to 45 degree. Now we'll apply equation of equilibrium in order to find the dx, dy, and this FBC, because here you can see you have these pins at point C and D. So what will be the equation of equilibrium? So we will, first equation of equilibrium is that sum of all moment about point E is equal to 0, and taking the counterclockwise moment as positive. So about point E, the first moment will be this dy, and perpendicular distance is 1.5 plus 1, 2.5, clear? And this is 2.5 meter, and this is producing counterclockwise movement, so it will be positive. So I will write dy into 2.5. Now you can see this FBC will have two components, one along x-axis, one along horizontal, clear. This component, if you resolve it into its rectangular component, and other one will be a vertical component. So this component will be equal to FBC sine of 45 degree, and this component will be FBC cos of 45 degree. Since this horizontal component is passing through point E, it is not producing moment, so only vertical force is producing moment, and this force into perpendicular distance is 1, and this is producing clockwise moment, so it will be negative. So I will write minus FBC sine of 45 degree is equal to 0. Perpendicular distance is 1, so I will also write multiply by 1 is equal to 0. So from here you will get 2.5 times dy is equal to minus sine of 45 is 0.707, so 0.707 FBC. That this is equal to 0, and that this equation is equation number 1. Now we'll apply another equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see one force is this one, which is FBC cos 45 degree, and second is this one. Their sum must be equal to 0. So I will write FBC cos of 45 degree minus dx is equal to 0. So from here, cos of 45 is 0.707, FBC minus dx will be equal to 0, and that this is your equation number 2. Now what we will do is that we will take the free body diagram of this ABD member. So let me write it. Take member ABD and draw its free body diagram. So remember this ABD, so I will draw it over here. So let this is your vertical member, clear. This is your point D, where you have horizontal dx, clear. You have vertical component which is dy. Let me draw it by using another color. This is your dy, clear. And at point D, it was also given that 4 kilonewton load is applied on member ABD. So let it makes this 4 kilonewton is this one. This is 4 kilonewton, and it is making an angle of 45 degree. That is given. And this is your point A, clear. This is at end your point A, and you have pin support, so you will be having a vertical reaction force, and this is represented as AY, as well as you will have a horizontal force which will be equal to AX. And at point B, this is your point B. So at point B, you can see you have member CB, which force here is shown. FBC is downward, so according to Newton's first law, this will apply force in this direction. Magnitude will remain same. So FBC will be in this direction. Okay, this is FBC, and this angle is 45 degree. This is 45 degree. So if you look at, so distance between D and B is 1.5, and this is also 1.5. So this distance is 1.5 meter, and this distance is also from B to A is also 1.5. So we will apply now equation of equilibrium in order to find this dx and dy. So what will be the equation of equilibrium? So we will apply the first equation of equilibrium is that sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. Okay, so what we will going is that you can see you have this FBC, it will have two component. One will be this component will be FBC cos of 45 degree, and one will be the vertical component which will be equal to FBC sine of 45 degree. Similarly, this 4 kilonewton will have two component, one along x-axis which will be equal to 4 cos of 45 degree, and one will be the vertical component, clear, which will be this vertical component will be 4 sine of 45 degree. Okay, now applying this equation of equilibrium, so this vertical component is passing through point A, it is not producing moments. These two forces are not producing moment because they are passing through it. So one component which is producing moment is dx, clear, the other one is 4 cos of 45, and third one is this FBC cos of 45. This component will produce moment. So I will start from this 4 into cos of 45, and perpendicular distance is 1.5 plus 1.5, and it is producing counterclockwise movement, so it will be positive. So 4 into cos of 45 multiplied by 3. So I will write 4 into cos of 45 degree multiplied by 3. The second force that is producing movement is this FBC cos of 45, and perpendicular distance is 1.5, and this is also producing counterclockwise, so it will be plus. So plus FBC cos of 45 degree, cos of 45 degree, clear, into perpendicular distance is 1.5. The third moment is due to this dx, and this dx into perpendicular distance is 3, and this is producing counterclockwise moment, clear, so it will be also positive. You can see here. Okay, so one thing you have to make correction, you can see here at point D you have taken dx in this direction for members ECD. So this on this member, this dx will be in opposite direction, so I will have to change this direction only. This dx will be in this direction. So this dx into perpendicular distance is this, and this is producing clockwise movement, so it will be negative. So I will write it minus dx into 3 is equal to 0. So now you can see this 4 cos of 45 multiplied 3 will give you 8.4852, plus this cos of 45 multiplied by 1.5 will give you 1.060, and there will be FBC minus 3 dx is equal to 0. Divide this equation by 3 to get dx, clear. So when you divide this by 3, so you will get 2.83 plus the second term will give you 0.35 FBC minus dx will be equal to 0. So from here you will get this dx will be equal to 2.83 plus 0.35 FBC. Let this is your equation number 3. So now what we will do is that put equation 3 in equation number 2. This is your equation number 2. You can see this is equation number 2. So 0.707 FBC minus 2.85 minus 0.35 FBC is equal to 0. So 0.707 BC minus this will give you 0.357 FBC is equal to 2.85. Okay, 2.85. So from here you will get this FBC will be equal to 8 kilonewton. 8 kilonewton. Now you have this FBC. So put value of FBC in equation number 1 and 2, clear, to get dx and dy. So you can see this is, you have to put the value of FBC over here and here, so you will get this dx and dy. So we for FBC is equal to 8 kilonewton in equation number 1. What is equation number 1? You can check it. Equation number 1 is this one, clear. This one is equation number 1. So when you put it, you will get dy will be equal to 2.263 kilonewton, and for FBC is equal to 8 kilonewton in equation number 2, you will get dx, and dx is 5.63 kilonewton. Now you can see dx and this is dx and this is dy. These are the two components, clear, and their net effect will be acting on this will act on this point D, and we will find this. You can see if I take it like this and this, so its net effect will be like this. So net will be like this. So we will find this by using Pythagoras theorem. So let me find that. Thus force acting on pin D is this FD, and that FD will be equal to dx square plus dy square under the root. So put the value 5.657 square, or this 5.63, you can take that plus 2.263 square under the root. So this FD will comes out to be 6.093 kilonewton. Now you can see that the net force acting on point D is FD, and this FBC is also there. So what we are going to do is that I will move to the next page. So first I will write, it is given that pin C is subjected to double shear. So if I draw this pin like this, clear? So this FBC was like this. This is FBC, which is 8 kilonewton. Let me show you over here. This is FBC, that is acting FBC, and that was 8 kilonewton. Let me show this is 8 kilonewton. So for double shear, it will be, the shearing will be like this, VC and VC. It is given this is double shear, so this 2 times VC is equal to FBC, clear? So this shear force, single shear, will be equal to FBC divided by 2. So 8 divided by 2 will give you 4 kilonewton, clear? And pin at D is subjected to single shear, that is given. So what does it mean? It means that if you have pin like this is straight, clear? So if net force acting at point D, which we have calculated, is FD, and that FD was 6.093 kilonewton. So single shear, so it will shear on one side. This will be VD. So here VD is equal to FD for single shear. Clear? I will divide it by 2. Okay. Now we have been given that allowable shearing stress, and we know that it is equal to V shear force divided by shearing area. Clear? So for C, for pin C, this allowable shearing stress is equal to shearing force at C divided by shearing area at C. So VC is 4 kilonewton. Clear? So 4 into 10 to the power 3 divided by shearing area. So shearing area is the area of pin is pi by 4 DC square. Clear? And that is equal to allowable shearing. And allowable shearing stress is given as 40 megapascal. Let me check it. 40 megapascal. So 40 into 10 to the power 6 is equal to 4 into 10 to the power 3 divided by pi by 4 DC square. So from here, this DC square is equal to 4 multiplied by 10 to the power 3 divided by pi by 4 into 40 multiplied by 10 to the power 6. And if you take square root on both sides, so you will get the DC diameter of pin at C will be equal to 0.01128 meter, or in millimeter, it will be equal to 11.3 millimeter. Now we'll find this diameter at pin D. So what we will go do is that allowable shearing stress is equal to VD divided by AD. So VD is 6.093 kilonewton divided by area, which is pi by 4 DD square. So from here you will get this DD square is equal to 6.093 into 10 to the power 3 divided by pi by 4, and pi allowable is 40 megapascal. So if you take square root on both sides, so you will get diameter of pin at D will be equal to 0.01393 meter, or in millimeter it will be equal to 13.9 millimeter, which is the answer of our this question. And that was all about this problem 1-84. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-83 that is taken from chapter number 1, Stress, and the book name is Mechanics of Material by R.C. Hibbeler. So statement is the 60 mm by 60 mm oak post is supported on the pine block if the allowable bearing stress for these materials are 43 megapascal for oak and allowable bearing stress for pine is 25 megapascal. Determine the greatest load P that can be supported. If a rigid bearing plate is used between these materials, determine its required area so that a maximum load P can be supported. What is that load? So you can see this is oak post and that is supported by pine block, clear? And there is a P load applied on it. So you have to, the allowable bearing stresses of both loads are given. So you have to find the largest load P that can be applied. And in B part, if there is a rigid bearing plate between these two, so you have to find the required area of this bearing plate for the maximum P load. So let's start with the solution. Now what we will do is that we will find this P for allowable bearing stress of this pine wood or pine block. We will find P. How we'll find P? So we know that stress is generally equal to force per unit area or load per unit area. So for this pine block, we are given this allowable stress for this pine is 25 megapascal. So 25 into 10 to the power 6 pascal. So this pine allowable bearing stress will be equal to load divided by bearing area. Clear? So load is not available. And you can see that it is mentioned that this is 60 by 60 millimeters. So this is 60 and this width is also 60. So this will be the bearing area. Clear? So I will write this is 60 by 60. So I will in meter it will be 0.06 multiplied by 0.06. And allowable bearing stress is 25 megapascal. So 25 into 10 to the power 6 is equal to P divided by 0.06 multiplied by 0.06. So from here you will get this P will be equal to 25 into 10 to the power 6 multiplied by 0.06 into 0.06. So when you multiply this, you will get 90 into 10 to the power 3 Newton, and in kilonewton it will be 90 kilonewton. So you will get this P. Now this P is calculated, that is based on allowable bearing stress of pine. Now what we will do is that we will find this P for allowable bearing stress of oak, and we will find P. So allowable bearing stress of oak is equal to load per unit bearing area. So load is not known and bearing area of this will be same as 0.06 0.06 multiplied by 0.06. And allowable bearing stress of oak is 43 megapascal. So I will write 43 into 10 to the power 6 will be equal to P divided by 0.06 multiplied by 0.06. So from here, this P will be equal to 43 into 10 to the power 6 multiplied by 0.06 multiplied by 0.06. And when you calculate it, it will be equal to 154.8 into 10 to the power 3 Newton, or in kilonewton, this P will be equal to 154.8 kilonewton. And you can round it off, so P will be equal to 155 kilonewton. Now you can see you have two loads. This is load based on pine, allowable bearing stress of pine, and this is the load based on allowable bearing stress of oak. And in question, we have been asked to determine the greatest load P. So our answer will be, answer of first part will be the greatest load P will be equal to 155 kilonewton. So this is answer of our first part. Now we will move towards second part, and in second part, it has been asked to find the bearing required area of bearing plate so that maximum load P can be applied. So if a bearing plate is incorporated in between these two wooden pieces, so what will be its bearing area? So what we will do is that you can take for this maximum load P, because it is given as maximum load P. So we know that, again, we know that stress is equal to load or force per unit area. So we will calculate this area of plate based on strength of pine. Why we are taking the strength of pine block? Because it is the smallest here. So we will design on the smallest one, smallest strength. So you can see this is the smallest and this is largest. So we'll choose this value. So the stress is 25 clear into 10 to the power 6 Pascal. Sorry, it will be Pascal. 25 into 10 to the power 6 is equal to P is the largest load. So 155 into 10 to the power 3 divided by the area. So from here you will get this area will be equal to 6.19 into 10 to the power minus 3, and unit will be square meter. So this is the answer of our second part. And that was all about this problem 1-83. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 1-85 that is taken from chapter number 1, stress, and book name is Mechanics of Materials by R.C. Hibbeler. So statement is the beam is made from southern pine and is supported by base plates resisting on the brickwork. If the allowable bearing stress for the materials are for pine, it is 2.81 ksi, and for brick, allowable bearing stress is 6.70 ksi. Determine the required length of the base plates at A and B to the nearest 1/4 inch in order to support the load shown. The plates are 3 inch wide. So you can see this is the beam here that is made up of southern pipe, and there is uniformly distributed load from one end till the over the whole length, that is 200 pound per feet, and there is a 6 skip load at a length of 5 feet from this point A, and there is a base plate between this beam and this bricks there. So you have to find the length of this base plate. So let's start with the solution. So first step is that if you remove this support at the brick, so there will be a reaction force. Let this reaction force is Ra, and if you remove this bricks, so there will be a reaction force offered by this brick on this beam or base plate, which will be Rb. Okay, now this 6 skip is equal to 6,000 pound. 6 skip is 6,000 pound, and when there is a uniformly distributed load of 200 feet, so when you convert this uniformly distributed load into a point load, so it will act at the half length of the beam, and this will be equal to 200 over the length which it acts. So total length is 13 feet. So 200 multiplied by 13 will give you 2,600 pounds feet, and it will act at the half. So total is 13. So it will be 6.5 from either sides. So this is 6.5 feet. Now we'll apply equation of equilibrium in order to find this Ra and Rb. So what will be the equation of equilibrium? So first equation of equilibrium, that sum of all moments about point A is equal to 0, and taking the counterclockwise movement as positive. So about this point A, the first movement will be due to this 6 skips or 6,000 pound load, and perpendicular distance is 5, and this is producing clockwise movement, so it will be negative. So I will write minus 6,000 into 5. The second movement is due to this load, and this is 2,600, and the perpendicular distance is 6.5, and this is producing clockwise, so it will be also negative. So I can write it minus 2,600 multiplied by 6.5. And the last load which is producing movement about point A will be Rb into perpendicular distance is 10 feet, and this is producing counterclockwise movement, so it will be positive. So I will write plus Rb multiplied by 10. And the sum of all movement about point A must be equal to 0. So from here we will get minus 30,000 minus this will be 16900 plus 10 Rb is equal to 0. So what we will get is that 10 Rb will be equal to 46,900, and this Rb will be equal to, if you divide 10 on both sides, so you will get 4690 pounds. So this is the value of Rb, reaction force by bricks at point B on the beam or base plate. Now you can find Ra by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So Ra is upward, so plus Ra plus Rb minus this 2,600 and minus 6,000, their sum must be equal to 0. So I can write Ra plus Rb minus 6,000 and minus 2,600 is equal to 0. So Ra plus Rb is 4690 minus 6,000 minus 2,600 is equal to 0. So when you calculate it, you will get Ra will be equal to 39 0.10 pounds. Now you have both RA and RB. So what we are going to do is that we will design this base plate. So what will be the parameters? So I will write the design must be based on the strength, and we will take the smallest strength, which is the strength of the pipe. So you have been given the allowable bearing stress of pine as well as for brake. So we will choose this value. Clear? This will be, and at point A, at A, first we will calculate for A. So at A, we know that bearing stress is equal to bearing load over per unit area. So at point A, you can see this load is offered on this bearing plate. Clear? So we will write it as RA divided by area of this plate at A. And the bearing, we have taken the strength of pine. So strength of pine is 2.81 KSI. So 2.81 into 10 to the power 3 is equal to RA, which is 3910. And area of base plate, if base plate is like this, the width is given. This width is 3 inch. Clear? And this length is not given. This length, which is length A. So I can write area will be equal to LA multiplied by 3. Clear? So from here you will get LA will be equal to 3910 divided by 2810 multiplied by 3. And when you calculate it, it will be equal to 0.464 inch. And if you can see that if length is 1, we have been given that L should be 1 over nearest to 1 over 4 inch, which is equal to 0.5 inch. And if L is equal to half inch, it is 0.5. This is 0.25. Okay. As our value 0.4 is near to this 0.5, so L we select, we use length of this base plate will be 1 over 2 inch. You can also write it 2 by 4 inch, which is again 1 over 2 inch. So length of this base plate is 1 over 2 inch. Now what we will do is that at point B, our base plate B, we know that stress is equal to RB divided by area. So from here the strength is 2.81 into 10 to the power 3 KSI. RB is calculated as 4690 divided by area of base plate. For B will be LB into 3 inch. So again this length LB will be equal to 4960 divided by 2810 multiplied by 3. And when you calculate it, it will be equal to 0.556 since inch. So LB is equal to 0.556 inch. And we will take it nearest to 1 over 4 inch. So this is 1 over 4, this is 1 by 2, and 3 by 4 is 0.75. So our value is in between these two. So and for the closer, our safer design will be 3 over 4 inch. So we will choose LB is equal to 3 over 4 inch. 3 over 4 inch. Which is the answer of our this question. So this length of this base plate should be half inch. Clear? And this length of this base plate should be 3 or 4 inch. And that was all about this problem 1-85. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. Problem 1-86. This problem is taken from chapter number 1, Stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the two aluminum rods supports the vertical force of 20 kilonewton. Determine their required diameters if allowable tensile stress for the aluminum is 150 megapascal. So you can see this is rod AB and this is rod AC that is acted upon by a 20 kilonewton load acts downwards. So due to this load, there will be a tensile stress in rod AB as well as in AC. And this rod AB makes an angle of 45 degrees with the horizontal. So you have to find the diameter of rod AB as well as diameter of rod AC. So let's start with the solution. So first step is that we will take this point A and we will draw the free body diagram. So P is acting downward. So this rod exert a force in this direction on point A, as well as this rod exert a force in this direction, which is FAC, and this is FAB. Clear? So we will draw the free body diagram. Free body diagram. So let this is your point A. Clear? This is A. So at A we have P, which is acting downward. This is rod, force in rod. The rod AB exert a force FAB at point A, and this makes an angle of 45 degree. Similarly, this rod AC will exert a force in this direction, FAC. Clear? And this is your point A. So we'll apply equation of equilibrium. So the first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see FAB will have two components. One component will be along x direction. Clear? One is x component. Clear? Which is FAB cos of 45 degree. And one will be its y component, which will be the vertical component. And this component will be FAB sine of 45 degree. So you can see one component which is FAB sine of 45 degree. Clear? And this P, which is 20 kilonewton, that is acting downward. Their sum must be equal to 0. So I will write minus 20 is equal to 0. So FAB will be equal to 20 divided by sine of 45 degree. And when you calculate this force, so force exerted by member AB at point A will be equal to 28.284 kilonewton. Now we will find this FAC by using equation of equilibrium. That sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So FAC is in opposite direction. So I will write minus FAC and this component FAB cos of 45 degrees in positive direction. So FAB cos of 45 degree is equal to 0. So FAC will be equal to FAB cos of 45 degrees. So FAB is 28.28 into cos of 45 degree. And when you calculate it, you will get this force offered by member AC at point A will be equal to 20 kilonewton. 20 kilonewton. Now these are the forces that is acted upon by this member on point A, and this member this exert a force in this direction and this exert force in this direction. As a result, due to Newton's third law, due to this load P, it will cause the tensile stresses in these rods. So we'll find this. We have been given that stress. We know that stress is equal to force per unit area. Clear? So we have been given allowable tensile stress is equal to force per unit area. So what we will do is that for rod AB, we have allowable stress is equal to FAB divided by area of rod AB. So we have allowable stress, which is 150 megapascal. So 150 into 10 to the power 6 is equal to FAB, which is 28.28 kilonewton. So kilo is converted into Newton, divided by, this is circular rod, so its area will be pi by 4 DAB square. So pi by 4 DAB square. So from here you will get DAB square is equal to 28.28 into 10 to the power 3 divided by pi by 4 into 150 multiplied by 10 to the power 6. And if you take square root on both sides, it's clear. So you will get diameter of rod AB will be equal to 0.0155 meter. And in millimeter, the diameter of rod AB will be equal to 15.5 millimeter. Sorry. Now we'll find for rod AC. So for rod AC, we have allowable tensile stress is equal to FAC divided by area of AC. So FAC is 20 kilonewton. So 20 into 10 to the power 3 divided by area is pi by 4. We are interested to find out diameter. So DAC square. Allowable stress is 150 megapascal. So 150 into 10 to the power 6 is equal to 20 into 10 to the power 3 divided by pi by 4 into DAC square. So from here, DAC square will be equal to 20 multiplied by 10 to the power 3 divided by pi by 4 multiplied by 150 into 10 to the power 6. And if you take square root on both sides, so you will get diameter of rod AC will be equal to 0.0130 meter, which is equal to 13 millimeter. And that is the answers of this question. So diameter of rod EB is 15.5, while diameter of rod AC is 13 millimeter for the above given load. And that was all about this problem 1-86. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-87 that is taken from chapter number 1, stress, and book name is Mechanics of Materials by R.C. Hibbeler. So statement is the two aluminum rods AB and AC having diameter of 10 mm and 8 mm respectively determine the largest vertical force P that can be supported. The allowable tensile stress for aluminum is 150 megapascal. So you can see this is rod AC and this is rod AB that is acted upon by a load of P. This remember AB makes angle 45 degree with the horizontal, and allowable tensile stress is 150 megapascal. So you have to find this P load that can be applied on this system. So let's start the solution. So you can see due to this force, there will be a normal load in rod AC and AB. So how we will find this? So let me write it. The normal force developed in member AB and AC can be determined by considering equilibrium of joint A. So what does it mean? It means that we will take joint A and we will apply equilibrium condition. So let this is your point A. So you can see at point A, the load due to this member AC will be FAC. Let this is FAC. You have P load that is acting downward, clear? And the load FAB, which is making an angle of 45 degree with the horizontal. So FAB. This makes 45 degree with the horizontal. So we'll find this FA and FAB and FAC by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force which is P acting downward. So I will write minus P. The other force which is the vertical component of this FAB. So this FAB will have two components. One is this one. This will be FAB cos of 45 degree. And the other one is vertical component which is FAB sine of 45 degree. So the other component, vertical component, is this one. So minus P plus FAB sine of 45 degree is equal to 0. So from here, this P will be equal to FAB sine of 45 degree. That this is equation number 1. Now we'll apply another equation of equilibrium at joint A, that is sum of all force along x direction must be equal to 0 and force in this direction taken as positive. So FAC is in negative direction. So FAC plus this FAB cos of 45 degree is equal to 0. So from here, you will get FAC is equal to FAB cos of 45 degree. And that this is equation number 2. Now we will calculate force P. First we will calculate force P due to allowable tensile stress and diameter DAB. So we know that allowable tensile stress is equal to force in rod AB divided by area of AB. So allowable bending stress is 150 megapascal. You can see this is 150 megapascal. So I will write 150 into 10 to the power 6 is equal to FAB, which is not known, divided by area of AB. So pi by 4, diameter of AB is given as 0.01 meters. So 0.01 whole square. Now we will multiply this pi by 4 into 0.01 square on both sides. So it will give us FAB. So when you calculate it, so you will get FAB will be equal to 11.78 kilonewton. Now put this FAB in equation number 1, which is P is equal to FAB sine of 45 degree. So 11.78 into sine of 45 degree will give you P. And this P will be equal to 8.33 kilonewton. And this P is based on allowable tensile stress in and diameter of rod AB. Now what we will do is that we will calculate this P for the rod AC. So allowable and diameter of AC, we will calculate P. So we know that allowable bending stress or tensile stress in rod AC will be FAC divided by area of AC. So that is 150 megapascal. So 150 10 to the power 6. FAC is not known, and diameter of AC is pi by 4 DAC, and DAC 0.008 square. You can check it. D of AC 0.0008. So from here, FAC will be equal to pi by 4 multiplied by 0.008 square multiplied by 150 into 10 to the power 6. So when you calculate it, you will get FAC will be equal to 7.540 kilonewton. Now put FAC in equation number 2. What is equation number 2? So equation number 2 is this one. So FAC will be equal to FAB cos of 45 degree, and from here we will get FAB is equal to FAC divided by cos of 45 degree. So put the value 7.540 divided by cos of 45 degree will give you FAB. Why we are calculating FAB? So this FAB will be equal to 10.66 kilonewton. We are finding FAB because FAB is equal to P divided by sine of 45 degree from equation number 1. So put FAB in equation number 1. So what was equation number 1 is that P is equal to FAB sine of 45 degree. So from here, P is equal to 10.66 into sine of 45 degree, and you will get P will be equal to 7.54 kilonewton. Now this P load is load due to diameter of AC and allowable tensile stress in rod AC. Now you have two value. One is this one and other one is this one. So what we will do is for safety purpose, we will choose the smallest one. Because it will be the safer. Choose P is equal to 7.54 kilonewton, which is the answer of this question. And that was all about this problem 1-87. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me.